Let's see an example on paging. Okay, so assume that there is a process, okay, which is size of 16 bytes only. Okay, the process size of 16 bytes, and there is a main memory size of 32 bytes. Okay, the total size of the main memory, your RAM is total 32 bytes, and your process, that is your software application program size, is 16 bytes. Okay, now this will be your 16 bytes of main memory. That is, let us take a process P1. Okay, this particular process Px, assume that Px, this particular Px process are is divided into A, B, C, D. So 4 bytes. So the page size of 4 bytes. So each page is consisting of 4 bytes of data. Okay, so system will divide the process into 4 bytes of that pages. Okay, and the physical memory is also divided into 4 bytes of frames, because frame size should be equal to page size. The physical memory is also divided into 4 bytes. So how many pages and how many frames will be there? Let's see. The formula for number of pages is process size divided by page size. Process size divided by page size. What is the process size? 16. 16 divided by 4, you will get 4 pages. Correct? The number of pages in the process is 4. 1, 2, 3, 4. Right? So this is P0, P1, P2, P3. Okay, right? Then number of frames will be, what is the number of frames? Main memory size by page size, that is 32 divided by 4, you will get 8 frames. Count it. This is 0, 1, 2, 3, 4, 5, 6, 7. Total 1, 2, 3, 4, 5, 6, 7, 8 frames. And you can name number it as F0, F1, F2, F3, F4, F5, F6, F7. Okay, so there is a process X, and these are the pages P0, P1, P2, P3 are pages, and F0, F1, F2, F3, so on up to F7 are frames. Okay, now we need to map this particular page number to, okay, page number to frame number, page number to frame number. So what CPU will do? CPU will generate a logical address of process. CPU will generate a logical address of process. Okay, what is mean by logical address? Suppose that how many bytes are here? 16 bytes. Okay, where the process resided actually? Hard disk. Okay, so this particular process, the addresses for every process, okay, the addresses are starts from 0, starts from 0, 0, 1, 2, 3, 4, 5, so on. So each process, every time for a different process, the address always starts from 0, 1, 2, 3, 5. Similarly, a physical memory, the addresses are not for every process, it is 0. So this is byte 0, byte 1, byte 2, byte 3, byte 4, byte 5, byte 6, byte 7, byte 8, byte 9, byte by 10, by 11. Okay, so that's why each frame will also have 4 bytes. Each frame will also have 4 bytes, but physical memory starts from 0 to its maximum size, that is 32 bytes. That means the last byte number will be 31. So total 32 bytes. Okay, so for this particular process, it is 0, 1, 2, 3, so on up to 16 bytes. So numbers will be 15. Numbers will be 15. Suppose that CPU requires this particular 9th memory byte, which is stored in the, where it is stored in main memory. Where it is stored in main memory? Okay, so that we need to find out. That we need to find out. So CPU generates the logical address of this one. What is the logical address that is generated out of 0 to 15? It is 9. Logical address that is generated, 9 is the byte number. Okay, 9. Now this particular 9, we need to convert it into page number and offset. Okay, page number and offset. Offset is the byte location in the page as well as the frame, because page number 0, offset 0, this is A, right? 0 is A, 1 is 2 B, 2 is C, 3 is D. Where it is located actually? Page number 0 is located in frame number 5. So look at it, the 0th position is A, First position is B, second position is C, third position is D. Okay, right? So let's divide this into page number and frame number. Divide this into page number and frame number. Okay, so page number and offset. Now, how to convert page number? Okay, logical address to page number. What is the logical address? 9. 9 divided by page size 4 bytes. 9 divided by 4, the quotient value will become 2. The quotient will become 2. Okay, so the page number equal to 2. I am changing this one to 2. 9, 2. Page number will become 2. When it comes to page offset, okay, page offset, it is 9 modulo 4. Okay, that means the remainder after you divide by 4, 9 modulo 4 is 1, because 4 to the 8 plus remainder 1, 1. Okay, that means that we have converted logical address to page number and offset value. But that means offset means within the page, what is the location of that particular logical address. Okay, location of the particular value. Now page number 2. Yes, page number 2. Okay, in the page number 2 there is 1. Okay, that is each page will be start numbering from 0 1 2 3. So in this particular page this is 0. Okay, so I will become 0, 0th entry, and J will become first entry, and K will become second one, L will become third one. Okay, that means it is first one. J is the one, so we require J. CPU requires J, but where is this particular J is stored in main memory? Where is this particular J is stored in main memory? You need to see page table. You need to see page table. Where is this page table? It is in the somewhere in the main memory, which is located by page table base register. Page table base register. There is a pointer. We'll see that particular address. We'll fetch the address and we'll see in the main memory. Now look at here. Page number 2. Where is page number 2? Here. Page number 2. And we need to find the corresponding frame number. Where is the frame number? So this row is your frame number. Page number 2, the corresponding frame number is 1. So you go to corresponding frame number. What is offset? 1. What is offset? 1. So this is 0 and this is 1. So where this particular J is stored? J is stored in fourth frame, first position. Okay, sorry, first F1. Okay, F1 first location. F1 first location. Okay, if you want to find the exact value of this one, if you want to find the exact byte number of this one in the main memory, okay, exact byte number, what is the logical address that is generated? 9. If you want the physical address of this one, if you want the physical address of this one, the conversion of logical address to physical address, you can find it that which is stored in the frame number and offset. Correct? Frame number and offset. What is the frame number I am getting? 1. And offset I am getting is also 1, because the offset of process is also same as offset in the frame. Okay, offset in the frame. Now multiply this one with page size, that is 1 into 4, 4, plus the displacement value 1. So it will be the fifth byte in the main memory. Okay, so this 5 is the physical address. This 5 is the physical address. That means we have converted logical address 9 to physical address 5. Logical address 9 to physical address 5. So this conversion is done at runtime. Okay, that means the logical address is divided into two parts. First one is page number, then offset. The physical address is divided into two parts again, that is frame number and offset. Okay, that is display. D means displacement. Okay, offset or displacement. This conversion of P to D to conversion of F to D, we will call it as binding, address binding. Okay, we'll call it as address binding. Okay, so CPU generates the logical address. It is a responsibility of memory management unit to convert the logical address to physical address. Okay, let's see the hardware support for this one. Okay, so let's see the hardware support. Paging hardware. Okay, so here CPU generates a logical address 9. Okay, so this particular logical address is divided into two comma 1, 2 comma 1. Now it will go to 0 1 2th entry, okay, second entry. Then it will find the page number 1. It will find the page number 1. So this frame, sorry, frame number 1. So this particular frame number is stored here 1, and the displacement value 1 value will be copied to here. So it will become 1 comma 1. Okay, so 1 comma 1, it will go to main memory, that is your physical memory, and you need to find the exact byte location. So this will be the frame number 1. Okay, this will be the frame number 1. So wait, that will be your frame number 1. Each frame is divided into 4 bytes: 1 2 3 4 5 6 7 8 9 10 11 12. Okay, divided into 4 bytes. Now you need to count it. You need to count it. Frame number 1, that is, this is 0 byte, 1 2 3 4 5 6 7 8 9 10 11. Okay, now 1 into page size, that is 4 plus 1, fifth location. So it will start from first, then 0 1 2 3 4, fifth location will be fetched and sent to CPU. Fetched and send it to CPU. Okay, so CPU says 9. Actually, the main memory byte number is 5. This particular physical byte value will be sent to CPU for execution. Okay, right? And I told you these page numbers and page tables and frame number tables are stored in the main memory. Okay, right? Now we need to see one more point, that every process will have a page table. Every process, if there are 100 processes in the system, then each and every process will have a page table. That means there will be 100 processes in the system. Okay, 100 processes in the system, there will be 100 page tables are created. Okay, but if there is a physical memory, there is one frame table. If you have two RAMs, there may be two. Okay, so there is a physical main memory, there is one frame table, but every process will have its own page table. Its own page table. Whenever one process went for CPU, that particular page table will be active, and all other remaining page tables will be deactive. Okay, the only the active process page table will be active by deactivating the remaining page tables. If there are 1,000 processes, each and every process will have its own page tables. Okay, as I told you, these page tables are stored in your main memory. Okay, right? So let's see one more address transfer.